Right now, something the size of a small mountain is racing through our solar system at speeds that shouldn't be possible, and scientists have completely lost sight of it. This thing is moving at over 58 kilometers per second, twice the velocity of anything we've ever tracked before. And it came from a direction that makes absolutely no sense. We've given it a name, 3I Atlas, and in just 4 months, astronomers have published nearly 100 research papers trying to figure out what this visitor actually is, because everything about it breaks the rules. If you want to see how this mystery unfolds, and why this could be the most important discovery in decades, smash that like button and subscribe, because this story gets even stranger. We're talking about an object that might be 7.5 billion years old, carrying secrets from before our planet even existed. And it's doing things that have never been observed in any comet ever. The sun is blocking our view right now during its closest approach. But when it reappears in December, we're going to get answers that could change everything we thought we knew about where comets come from and what else is out there in the darkness between stars. Prepare yourselves. We begin. The story of 3I Atlas begins on the night of July 1st, 2025, when a network of telescopes scattered across the globe locked onto something moving through the darkness, and what they found would send shockwaves through the astronomical community, because this wasn't just another space rock drifting through our cosmic neighborhood. The Asteroid Terrestrial Impact Last Alert System, which goes by the acronym ATLAS, operates a series of powerful telescopes positioned strategically around the world in places like Rio Hurtado, Chile, Hawaii, and South Africa, and their entire purpose is to scan the night sky looking for anything that moves, which is how they protect us from potential asteroid impacts that could threaten our planet. These telescopes work tirelessly every single night, capturing image after image of the same patches of sky, then comparing those images to detect even the slightest movement of an object against the background of distant stars. And on this particular night, in early July, the ATLAS telescope in Chile caught something unusual between the hours of 5:15 in the morning and 6:20 in the morning, capturing 4 separate exposures that showed a faint dot of light moving across the field of view. At first, the team classified it as just another asteroid, which is a pretty routine discovery because ATLAS finds asteroids all the time, and they've got a whole system for cataloging these objects, giving them temporary designations, calculating their orbits, and then moving on to the next target. But then someone on the team decided to take a closer look at the velocity of this particular object. And that's when everything changed, because when they ran the calculations on how fast this thing was actually moving, the numbers didn't make any sense at all. To understand why the astronomers were so shocked, you need to understand how motion works in our solar system, because everything out here is governed by the same fundamental force that keeps your feet planted on the ground, and that's gravity. The sun sits at the center of our solar system, with a mass so enormous that it creates a gravitational well, which you can think of like a massive invisible funnel in the fabric of space. And every planet, moon, asteroid, and comet is constantly falling into that funnel. But the reason we don't actually fall into the sun is because we're also moving sideways at tremendous speeds, and that sideways motion keeps us in orbit, just like when you spin a bucket of water over your head and the water stays inside even though it's upside down. The closer you get to the sun, the deeper you are in that gravitational well, which means you need to move faster and faster to avoid falling in. And we can use Earth as our baseline here, because we're orbiting at a pretty decent clip of 30 kilometers per second, which is about 67,000 miles per hour, fast enough to circle the entire planet in less than 7 minutes. Mercury, being much closer to the sun, at only 0.4 astronomical units away, which is the distance measurement we use, where 1 astronomical unit equals the average distance between Earth and the sun, has to orbit at a blistering 48 kilometers per second, just to stay afloat in that intense gravitational field. And if it slowed down even a little bit, it would spiral into the sun and get vaporized. Now here's where things get absolutely wild, because when the Atlas team calculated the velocity of this new object they'd just discovered, they clocked it moving at 58 kilometers per second. And remember, this thing was spotted way out beyond the orbit of Mars, at around 4.5 astronomical units from the Sun, which is more than 10 times farther out than Mercury. And yet it was moving faster than Mercury, despite being in a region where the Sun's gravitational pull is much weaker. That speed told astronomers something extraordinary, because there's a specific velocity threshold called escape velocity, and if an object reaches that speed, it can break free from the Sun's gravity entirely and fly off into interstellar space, never to return. And the calculations showed that this object had already exceeded escape velocity by a massive margin. This wasn't something that had formed in our solar system and gotten knocked loose by a collision or a gravitational encounter with a planet, because objects from our solar system that get ejected typically do so at speeds just barely above escape velocity. But this thing was moving with such tremendous speed that it could only mean one thing, and that one thing completely changed the nature of the discovery. This object had come from interstellar space, from the vast emptiness between the stars, and it was just passing through our solar system on what astronomers call a hyperbolic trajectory, meaning it would swing past the Sun in a wide arc and then continue right back out into the void, and we would never see it again. The realization hit the astronomical community like a lightning bolt, because interstellar objects are incredibly rare, and up until this discovery, we had only ever confirmed 2 others in the entire history of astronomy. The first one, which you've probably heard of, was Oumuamua, discovered in October 2017 by the Pan-STARRS telescope in Hawaii, and that object became famous not just because it was the first confirmed interstellar visitor, but also because of how weird it was, with its elongated cigar shape and the way it seemed to accelerate as it left the solar system, without showing any signs of the comet activity that would explain that acceleration, which led to all sorts of wild speculation and debates that continue to this day. Then in August 2019, we discovered the second interstellar object, 2I Borisov, which was spotted by amateur astronomer Gennady Borisov using a telescope he built himself in Crimea. And unlike its predecessor, Borisov acted pretty much exactly like a normal comet, with a bright coma and a tail, and all the characteristics we expected, so it was almost weirdly normal for something that had traveled from another star system. Now we had a third confirmed interstellar visitor, and the Minor Planet Center, which is the official organization responsible for designating and tracking small bodies in the solar system, announced the discovery on July 2nd, 2025, giving it the designation 3I/ATAA, where the 3I stands for Third Interstellar Object, and ATAA references the telescope system that found it. They also gave it the alternate designation C/2025 N1ATAA, using the standard naming convention for comets, but everyone just calls it 3I Atlas because that name captures what makes it so special. By the time the official announcement went out, astronomers had already started digging through archives of telescope data to see if anyone had accidentally photographed this object before it was officially discovered. And sure enough, they found pre-discovery images from all over the world. The Zwicky Transient Facility at Caltech's Palomar Observatory in California had captured it, and most incredibly, NASA's Transiting Exoplanet Survey satellite, known as TESS, which orbits Earth and normally spends its time hunting for planets around distant stars, had actually been looking in the right direction at the right time and had recorded 3I Atlas moving through space between May 7th and June 3rd, 2025, which means we'd been looking at this object for nearly 2 months before anyone realized what it was. The Vera C. Rubin Observatory, which had just started its science validation phase, had also serendipitously imaged 3I Atlas between June 21st and July 3rd during its test observations. And astronomers later realized that if the Rubin Observatory had started those test observations just 2 weeks earlier, they would have been the ones to officially discover this interstellar visitor instead of Atlas. Once word got out about the discovery, telescopes all around the world immediately started pointing at 3I Atlas to gather as much data as possible, because opportunities like this don't come along very often. And by the time the object was officially named, the Minor Planet Center had already collected 122 separate observations from 31 different observatories, scattered across multiple continents. The sheer speed of 3I Atlas became one of the first major talking points, because at 58 kilometers per second, this thing was moving at roughly double the velocity of both Oumuamua and Borisov, which had cruised through our solar system at a comparatively leisurely 30 kilometers per second. And that immediately raised questions about where this object came from and what kind of cosmic event could have launched it through space at such incredible speeds. To put that velocity into perspective that humans can actually wrap their heads around, 58 kilometers per second translates to about 130,000 miles per hour, which means this object could travel from Los Angeles to New York in about 87 seconds, or it could circle the entire Earth at the equator in roughly 11.5 minutes. And it's maintaining that speed while traveling through the vacuum of space where there's no air resistance to slow it down. The discovery also revealed something else that would become increasingly important as observations continued, and that was the object's size, because based on the amount of light it was reflecting and the distance at which it was spotted, astronomers estimated that 3I Atlas could be anywhere from 3 to 5.6 kilometers wide, which makes it significantly larger than both of its interstellar predecessors. Oumuamua was estimated to be only about 400 meters across at its longest dimension, roughly the length of 4 football fields, while Borisov measured about 1 kilometer in diameter, so 3I Atlas dwarfs them both, and a 5.6 kilometer wide object is genuinely massive on the scale of comets and asteroids, comparable in size to some of the larger objects in the asteroid belt between Mars and Jupiter. That size, combined with the extreme velocity, meant that 3I Atlas was carrying an absolutely enormous amount of kinetic energy. And if it were on a collision course with Earth, which thankfully it absolutely was not, the impact would be catastrophic beyond anything in recorded human history. But the calculations clearly showed it would pass nowhere near our planet, staying safely at a distance of about 1.8 astronomical units at its closest approach in December, which is roughly 167 million miles away. The Atlas team had done their job perfectly, identifying a fast-moving object and determining that it posed no threat to Earth. But what they'd really discovered was so much more than just another asteroid to catalog, because this was a visitor from beyond our solar system, an ancient wanderer that had been traveling through the galaxy for billions of years before randomly passing through our little corner of space. And the fact that we spotted it at all was an incredible stroke of luck. The discovery triggered an immediate response from the global astronomical community, because everyone wanted a piece of this object before it disappeared forever. And within days, some of the most powerful telescopes on and around Earth were being retasked to observe 3I Atlas, including the Hubble Space Telescope, which captured its first images on July 21st, 2025, when the comet was 277 million miles from Earth, showing a bright fuzzy object with a distinct coma already forming around it. The James Webb Space Telescope, humanity's most advanced space observatory, made its first observations using its near-infrared spectrograph instrument on August 6th, and NASA announced those initial findings on August 25th, giving scientists their first detailed look at the chemical composition of material being ejected from the comet's surface. Observatories on the ground joined the effort as well, with facilities like the Comet Astronomical Observatory in Egypt using its 1.88-meter telescope, the iconic Palomar 200-inch telescope in California, and the Apache Point Observatory's 3.5-meter telescope in New Mexico, all capturing detailed images and spectra that would help piece together the mystery of what this object was and where it came from. The James Clerk Maxwell Telescope in Hawaii, which specializes in sub-millimeter wavelength observations, observed 3I Atlas on September 7, 2025, when the comet was 2.33 astronomical units from the Sun, and they detected hydrogen cyanide molecules being ejected at a rate of 1.5 times 10 to the 25th power molecules per second. And when they looked again, just 1 week later, on September 14th, that production rate had jumped to 4.5 times 10 to the 25th power molecules per second, which equals about 2 kilograms of hydrogen cyanide being blasted into space every single second, showing that the comet's activity was rapidly increasing as it got closer to the Sun. By the end of the summer of 2025, in just the first 4 months after the discovery was announced, astronomers had published nearly 100 research papers about 3 Atlas, analyzing everything from its trajectory and velocity to its chemical composition and the strange behavior it was exhibiting. And that unprecedented level of scientific attention reflected just how important this discovery was to our understanding of interstellar objects and the broader universe. The speed alone would have been enough to make 3I Atlas interesting, but it was just the beginning of a long list of anomalies that would make this the weirdest and most mysterious interstellar visitor we've ever encountered. And as telescopes continued to track it through the summer and fall of 2025, each new observation seemed to reveal something that didn't quite fit with our expectations of how comets are supposed to behave, building a picture of an object that was simultaneously familiar and completely alien, something that had formed in a solar system with very different conditions from our own, and had been wandering through the darkness of interstellar space for billions of years before fate brought it within range of our telescopes for this brief cosmic moment. The speed of 3I Atlas was shocking enough to get astronomers talking, but when they started analyzing the trajectory, the direction this thing was traveling from, they realized they were dealing with something that bordered on impossible, because space is three-dimensional and an object from interstellar space could approach our solar system from literally any direction across the entire celestial sphere. And yet, 3I Atlas managed to hit us in the one direction that seemed almost too perfect to be coincidental. To understand why this trajectory is so mind-blowing, we need to talk about the 2 interstellar visitors that came before it, starting with Oumuamua, which entered our solar system in September 2017 from the direction of the constellation Lyra, approaching from what astronomers call the northern sky. And when they plotted its path, they realized it was coming from roughly the same direction that our entire solar system is moving as we orbit around the center of the Milky Way galaxy. You see, we tend to think of the solar system as this static thing, with planets orbiting the sun, and the sun just sitting there in one place. But that's not accurate at all, because the sun itself is in motion, racing through space at about 230 kilometers per second as it completes one massive orbit around the galactic center, a journey that takes approximately 230 million years. And as the sun moves, it drags all of us along with it, the planets, the asteroid belt, the Kuiper belt, everything in its gravitational influence. So when Oumuamua came in from the northern sky, it was almost like we ran into it head-on, like 2 cars approaching an intersection from different streets. And the collision wasn't perfectly straight on, but more at an angle, which is why Oumuamua's trajectory was inclined about 122 degrees relative to the ecliptic plane, which is the flat disk where all the planets orbit. Then came 2I Borisov in August 2019, discovered by amateur astronomer Gennady Borisov from Crimea. And when astronomers traced its path, they found it also came from the northern sky, specifically from the direction of the constellation Cassiopeia, approaching at an angle that was similar to Oumuamua, though not identical, with an orbital inclination of about 44 degrees, meaning it came in from above the ecliptic plane, but at more of a diagonal angle than Oumuamua's steeper approach. Both of these interstellar visitors followed what you might call a logical pattern, because if you're a solar system moving through the galaxy, you're going to encounter more stuff coming from the direction you're heading toward, just like when you're driving through a rainstorm and more raindrops hit your windshield than your rear window, because you're driving into them. This made sense and fit with what scientists expected from interstellar objects randomly drifting through the galaxy. But then, 3I Atlas showed up and completely shattered that pattern, because instead of coming from the northern sky, from the direction we're moving, it came from the side, and not just vaguely from the side, but in almost perfect alignment with the ecliptic plane itself, making this an absolute cosmic rarity. The ecliptic plane is the thin disk of our solar system, where all the major planets orbit. And it formed billions of years ago, when our solar system was just a massive rotating cloud of gas and dust that collapsed under its own gravity. And as that cloud collapsed, it spun faster and faster, and centrifugal force caused it to flatten out into a disk shape, just like how pizza dough flattens when you spin it in the air. All the material in that disk eventually clumped together through countless collisions over millions of years, forming the sun in the center, and the planets, moons, and asteroids in the surrounding disk. And because everything formed from the same rotating cloud, almost everything in our solar system orbits in roughly the same flat plane, like grooves on a vinyl record. When astronomers measure how tilted an object's orbit is relative to this ecliptic plane, they use something called orbital inclination, measured in degrees, where 0 degrees means perfect alignment with the plane, and 90 degrees means the object is orbiting perpendicular to the plane, moving straight up and down rather than around. Most planets have orbital inclinations very close to 0 degrees, because they all formed from that same original disk, with Earth obviously at 0 degrees. By definition, since Earth's orbit is what defines the ecliptic plane, and Mercury at 7 degrees, Venus at 3.4 degrees, Mars at 1.9 degrees, Jupiter at 1.3 degrees, and Saturn at 2.5 degrees. Even the outer planets stay pretty close to the plane, with Uranus at 0.8 degrees and Neptune at 1.8 degrees. So when you look at the solar system edge on, it really does look like a flat disk with all these worlds circling the sun in the same general plane. There are a few notable exceptions, objects whose orbits are significantly tilted, and the most famous one is Pluto, which has an orbital inclination of 17.1 degrees, meaning its orbit is tilted enough that sometimes it's noticeably above the ecliptic plane and sometimes it's noticeably below it. And this tilted orbit was actually one of the factors that contributed to Pluto's controversial demotion from planet status to dwarf planet back in 2006. Some asteroids and comets from the Kuiper Belt and the Oort cloud also have tilted orbits, with inclinations ranging anywhere from a few degrees to 45 degrees, or even more in some extreme cases. And these tilted orbits usually result from gravitational interactions with the giant planets, particularly Jupiter and Neptune, which can fling smaller objects into weird trajectories over millions of years. But here's the thing. Even the most tilted objects in our solar system are nowhere close to the extreme inclinations we saw with Oumuamua and Borisov, which came plunging through our solar system at angles that made it immediately obvious they were interstellar visitors, because nothing that formed here naturally gets tilted that severely, unless it's had an incredibly violent encounter with multiple planets, which would probably destroy it in the process. So scientists expected that interstellar objects would have high inclinations because they're not bound by the same formation history that shaped our solar system, and they expected those objects to come from random directions across the sky. And the first two interstellar visitors fit that expectation perfectly. But 3I Atlas decided to do something completely different. When astronomers calculated the orbital inclination of 3I Atlas, they found it was traveling at an angle of only 3 degrees relative to the ecliptic plane. And to put that in perspective, that's less tilted than Venus, less tilted than Mercury, and only slightly more tilted than Mars, making this interstellar visitor more aligned with our solar system's planetary disk than several objects that actually formed here. The trajectory analysis showed that 3I Atlas was moving in what's called a retrograde direction, meaning it's orbiting in the opposite direction from the planets, coming in from the side and moving against the flow of traffic like a wrong-way driver on a highway. But even with that retrograde motion, the 3-degree inclination meant this object was threading the needle through our solar system, almost perfectly edge-on with the planetary disk. To really appreciate how weird this is, imagine the solar system as a giant frisbee flying through space, with the sun at the center and all the planets as little dots spinning around on the surface of the frisbee. And now imagine that space around the frisbee is a complete sphere in 3 dimensions, meaning an interstellar object could approach from any point on that sphere, from above, from below, from the side, from any angle in between, and the total possible approaches number in the thousands when you account for all the different angles and trajectories. Out of all those possible approaches, 3I Atlas chose to come in almost perfectly aligned with the flat plane of the frisbee, hitting us edge-on in a trajectory that astronomers calculate had less than a 1% probability of happening by random chance. And yet here it was, and nobody could quite explain why. Some researchers started speculating about whether this alignment could tell us something about where the object came from. Because if it originated in another solar system that happened to have a similar orientation to ours, maybe it got ejected in a way that preserved that alignment. But the problem with that theory is that over the billions of years this object has been traveling through interstellar space. Random gravitational interactions with other stars should have randomized its trajectory, tumbling it in different directions and erasing any memory of its original orientation. The alignment becomes even more fascinating when you consider that 3I Atlas didn't just come in aligned with the ecliptic plane. It came from the specific direction of the galactic core, the bright central bulge of the Milky Way galaxy, where stars are packed much more densely than in our neighborhood, out in the spiral arms. If you look at a picture of the Milky Way from the typical top-down view that you see in astronomy textbooks, you can see the beautiful spiral arms radiating out from the central bulge, and our solar system sits about 26,000 light-years from the galactic center, roughly halfway between the core and the outer edge of the galaxy, nestled in a relatively quiet region called the Orion Spur, which is a minor spiral arm branching off from the larger Perseus arm. When you look up at the night sky on a clear night away from city lights, that bright band of stars you see stretching across the sky is the Milky Way, and you're actually looking toward the next spiral arm over from us, seeing the combined light of billions of stars concentrated in that direction. But the galactic core itself is located in the direction of the constellation Sagittarius, and that's roughly the direction 3I Atlas came from, traveling outward from the inner regions of the galaxy toward the outer regions where we live. Now, the galaxy isn't just a flat disk any more than our solar system is just a flat disk, because while most stars are concentrated in a thin disk around the galactic center, there are also stars above and below that disk, in what astronomers call the thick disk and the galactic halo. And these regions are populated by older stars that formed in the early history of the galaxy, before everything had fully settled into the flat spinning disk we see today. When astronomers flipped their view of the galaxy to look at it edge-on instead of top-down, they could see that 3I Atlas most likely originated from this thick disk region, an area above or below the main galactic plane, where stars are older, more spread out, and less disturbed by the violent processes happening in the densely packed main disk. Processes like supernova explosions and collisions between stellar systems and gravitational interactions that can fling planets and comets out of their home systems. The thick disk is like the galactic suburbs, a quieter neighborhood where things have remained relatively unchanged for billions of years. And based on the trajectory and estimated age of 3 Atlas, astronomers believe this object could have been wandering through that region for as long as 7.6 billion years, which would make it nearly twice as old as Earth and significantly older than our entire solar system, which formed about 4.6 billion years ago. To put that age into perspective, when 3 Atlas first formed in whatever distant stellar system gave birth to it, our sun didn't exist yet. There was just a massive cloud of gas and dust floating in space in this region of the galaxy, and that cloud wouldn't collapse and ignite for another 3 billion years, and Earth wouldn't form for another 4.5 billion years after that, and life wouldn't emerge on Earth until billions of years after that. And all the while, this ancient comet was just drifting silently through the void, untouched and unchanging, carrying with it pristine material from a long-dead star system that no human will ever be able to identify or study. The realization that 3I Atlas could be this ancient makes it one of the most scientifically valuable objects we've ever had the opportunity to study, because it's essentially a time capsule from the early era of our galaxy, when the Milky Way was younger and still assembling itself into the structure we see today. And the material in this comet might contain clues about what conditions were like in that ancient epoch, what elements were abundant, what kinds of ices and minerals formed around stars back then, how different the chemistry of planet formation might have been in the early galaxy, compared to what we see around young stars today. Getting back to the trajectory, astronomers use sophisticated computer simulations to backtrack the path of 3I Atlas through space, rewinding its motion through time to see if they could identify any stars it might have passed close to on its long journey. And what they found was both fascinating and frustrating, because even when they rewound the trajectory 10 million years into the past, tracing it backward through the galaxy, as both the comet and the nearby stars moved through their respective orbits around the galactic center, they found that 3I Atlas had encountered 93 different stars during that time period. But the closest it had come to any of those stars was a distance of 0.3 light-years, which equals about 63,000 astronomical units. Remember, right now 3I Atlas is just 1.4 astronomical units from our Sun, so even its closest stellar encounter over the past 10 million years was more than 45,000 times farther away than it currently is from us. And at that distance, the gravitational influence of those stars would have been essentially negligible, not nearly strong enough to significantly alter the comet's trajectory or to explain where it came from originally. This means that over at least the past 10 million years, 3I Atlas has been traveling through the vast emptiness between stars, not gravitationally bound to any particular stellar system, just drifting along with the general motion of stars in the thick disk region of the galaxy. And the fact that it happened to pass this close to our Sun is purely a matter of cosmic chance, like two ships passing in the night, in an ocean so vast that most ships never see another vessel in their entire existence. The trajectory analysis also revealed something else that added to the mystery, and that was the exact angle at which 3I Atlas crossed the ecliptic plane. Because it didn't just come in aligned with the plane, it came in moving, almost perpendicular to the direction our solar system is traveling, hitting us from the side, in what collision investigators would call a T-bone impact, where one vehicle hits another at a 90-degree angle at an intersection. If our solar system is a car driving north through the galaxy at 230 kilometers per second, 3I Atlas came in from the east, traveling at its own tremendous velocity, and the two trajectories intersected at just the right place and time for us to detect it, a cosmic intersection that required incredibly precise timing, because if 3I Atlas had passed through this region of space just a few thousand years earlier or later, it would have missed our solar system entirely, passing harmlessly through empty space without ever coming close enough to any planet or the Sun for our telescopes to spot it. Some astronomers have wondered whether the nearly perfect ecliptic alignment and the sideways approach angle might be connected somehow, whether there's some underlying physics or galactic structure that makes this type of trajectory more common than we think. But so far, nobody has come up with a convincing explanation, and the current consensus is that this is just an extraordinary coincidence, a 1-in-1,000 shot that happened to occur during the brief period of human history when we have the technology to detect and study it. The trajectory of 3I Atlas is officially described as hyperbolic with an orbital eccentricity greater than 1, which is the mathematical way of saying this object is not gravitationally bound to the Sun and will escape the solar system after completing its current pass. And the specific eccentricity calculated for 3I Atlas is about 3.3, meaning it has more than enough velocity to break free of the Sun's gravity and return to interstellar space. And unlike objects with elliptical orbits that loop back around the Sun in recurring cycles, hyperbolic trajectories are one and done, a single pass through the solar system before departing forever. The closest point in 3I Atlas's trajectory to the Sun, called Perihelion, occurred on October 29, 2025, when the comet passed within 1.36 astronomical units of our star, which equals about 203 million kilometers, or 126 million miles. And to put that distance in context, it's roughly the same as the distance between the Sun and Mars, well outside Earth's orbit, and nowhere near close enough to pose any threat to our planet. At perihelion, 3I Atlas was moving at its maximum velocity relative to the Sun, screaming past at 68 kilometers per second, which is even faster than the 58 kilometers per second it was traveling when first discovered back in July. And that increase in speed makes perfect sense because as the comet fell deeper into the Sun's gravitational well, it accelerated just like a ball rolling down a hill, speeds up as it descends, and then after passing perihelion, it will begin to slow down gradually as it climbs back out of that gravitational well on its way out of the solar system. The trajectory will bring 3I Atlas relatively close to several planets, though not close enough for any gravitational interactions that would significantly alter its path. And the first close approach already happened on October 3, 2025, when the comet passed within 0.19 astronomical units of Mars, which is about 29 million kilometers or 18 million miles, making Mars the planet that got the closest view of this interstellar visitor. And that proximity was incredibly fortunate for scientists, because we have multiple spacecraft currently operating at Mars, including orbiters and rovers, with cameras that could capture images of the comet from a much closer vantage point than anything on or near Earth. After passing Mars, 3I Atlas continued inward toward perihelion, and then after rounding the Sun, it will make its closest approach to Earth on December 19, 2025, passing at a distance of 1.8 astronomical units, which equals about 270 million kilometers, or 167 million miles. And even though that's the closest it gets to us, it's still much farther away than the Sun is from Earth, so there's absolutely zero danger of any collision or impact. And in fact, the comet will be so far away that it won't even be visible to the naked eye, requiring at least a decent amateur telescope to spot it, and only for a brief window before it becomes too faint to see. The final close planetary encounter will occur on March 16, 2026, when 3I Atlas passes within 0.36 astronomical units of Jupiter. And that encounter is particularly interesting because Jupiter is such a massive planet with such strong gravity that it can sometimes deflect objects onto different trajectories. But in this case, 3I Atlas is moving so fast and passing at just enough distance that Jupiter's gravity will barely affect it, maybe tweaking its trajectory by a tiny fraction of a degree, but not enough to keep the comet trapped in the solar system or to fling it onto some dramatically different path. By the time 3I Atlas reaches Jupiter, it will be much farther from the Sun, cooling down and becoming less active, and the tail that may have formed around perihelion will likely have faded or disappeared entirely, and the comet will look more like a dim, slow-moving point of light than the spectacular fuzzy object with a tail that we typically associate with comets. But scientists will still be watching it carefully, because NASA's Juno spacecraft is currently orbiting Jupiter, and there's a possibility that Juno could be tasked with capturing one final image of this interstellar visitor before it disappears into the darkness forever. After the Jupiter flyby, 3I Atlas will continue outward through the outer solar system, passing through the orbits of Saturn, Uranus, and Neptune over the following years, though it won't come particularly close to any of those planets. And eventually, sometime around January 2026, it will cross the boundary that astronomers generally consider to be the edge of the Sun's gravitational influence, a distance of about 2 astronomical units from the Sun, where the solar wind starts to fade and the interstellar medium begins to dominate. And at that point, 3I Atlas will officially return to interstellar space, resuming its billion-year journey through the galaxy, perhaps eventually passing through another star system, billions of years from now, where if intelligent beings exist there, they might detect it and marvel at this ancient wanderer, just as we are doing now. When astronomers started trying to figure out where 3I Atlas actually came from, they faced a challenge that sounds simple on the surface, but quickly becomes incredibly complex, because tracking an object backward through time across millions or even billions of years of galactic history requires accounting for countless gravitational interactions and the chaotic motion of hundreds of billions of stars, all orbiting around the center of the Milky Way galaxy at different speeds and in different directions. And even with the most powerful supercomputers and the best data available, you can only rewind so far before the uncertainties pile up and make any specific conclusions impossible. But what astronomers could determine with reasonable confidence is that 3I Atlas came from somewhere in the inner regions of the galaxy, specifically from the direction of the galactic core. And that simple fact immediately tells us something profound about the age and nature of this object. Because the architecture of our galaxy isn't random. It's structured in a way that reflects billions of years of cosmic history. When you look at images of the Milky Way from the classic top-down perspective that shows up in astronomy books and documentaries, you see a beautiful spiral galaxy with long, elegant arms radiating out from a bright central bulge. And these spiral arms are where most of the action happens in our galaxy, where clouds of gas and dust collapse to form new stars, where massive stars live their brief, violent lives before exploding as supernovas, where stellar nurseries glow with the light of thousands of newborn stars. And our Sun sits in one of these spiral arms about 26,000 light-years from the galactic center, roughly halfway between the core and the outer edge. But that top-down view only tells part of the story, because galaxies are three-dimensional structures, and when you flip the Milky Way on its side to look at it edge-on, you see something different, a thin disk containing most of the visible stars and gas, surrounded by a thicker, more diffuse region that extends above and below that main disk. And these different regions have very different characteristics in terms of the age of their stars, their chemical composition, and their motion through space. The thin disk, which contains about 85% of all the stars in our galaxy, including our Sun, is where most star formation happens today. And it's relatively flat, only about 1,000 light-years thick at our location in the galaxy, though it gets thinner toward the outer edges and thicker toward the center. The stars in the thin disk are what astronomers call population 1 stars, which means they're relatively young by cosmic standards, ranging from newborns that formed just a few million years ago to middle-aged stars, like our Sun, that formed about 4.6 billion years ago. And these stars are metal-rich, which in astronomy means they contain significant amounts of elements heavier than hydrogen and helium, elements like carbon, oxygen, nitrogen, iron, and silicon. Now you might wonder why younger stars would be metal-rich when the universe started with only hydrogen and helium after the Big Bang. And the answer is that every generation of stars produces heavy elements in their cores through nuclear fusion. And when those stars die, especially when massive stars explode as supernovas, they blast those heavy elements out into space, where they get incorporated into the next generation of stars. So stars are like cosmic recycling centers, and each new generation is slightly more metal-rich than the one before. The thick disk, by contrast, is a much larger and more diffuse structure that wraps around the thin disk like a puffy cushion, extending about 2,000 to 3,000 light-years above and below the galactic plane, and it contains only about 10 to 15% of the galaxy's stars. But those stars are fundamentally different from the ones in the thin disk. Thick disk stars are what astronomers call population 2 stars, which means they're old, typically ranging from 8 billion to 12 billion years old, making them some of the oldest objects in the galaxy, formed when the Milky Way itself was still young and actively assembling from smaller proto-galactic fragments. These ancient stars are metal-poor compared to thin disk stars because they formed from gas that hadn't been enriched by as many previous generations of stars, so their chemical composition is closer to the primordial mix of elements that existed in the early universe, dominated by hydrogen and helium, with only trace amounts of heavier elements. The thick disk is also kinematically distinct, which is a fancy way of saying the stars in it move differently than thin disk stars, because while thin disk stars generally orbit the galactic center in nice circular paths, all going in the same direction, like cars on a racetrack, thick disk stars have much more chaotic orbits, tilted at various angles to the galactic plane, and often moving in elliptical paths that carry them far above and below the main disk, before looping back down. And these weird orbits are thought to be the result of violent gravitational interactions that happened billions of years ago, when the Milky Way was still forming and smaller galaxies were merging into it, stirring up the stellar populations like cream swirling through coffee. When scientists analyzed the velocity and trajectory of 3 Atlas, they noticed something unusual, which was that the comet's motion perpendicular to the galactic plane, what astronomers call the W velocity component, was unusually high compared to most stars in our local neighborhood. And this high vertical velocity indicated that 3 Atlas follows a tilted orbit around the galactic center, an orbit that carries it above and below the main galactic plane, rather than staying confined to the thin disk, and that type of orbit is characteristic of thick disk objects. A team of researchers, led by Matthew Hopkins at the University of Oxford, conducted a detailed analysis of 3 Atlas's trajectory and published their findings in a paper that made a startling claim, suggesting that this interstellar comet is the first known object from outside our solar system that definitely originated in the thick disk population of the Milky Way, which would make it fundamentally different from the 2 previous interstellar visitors, Oumuamua and Borisov, both of which appeared to come from thin disk populations based on their trajectories and velocities. If 3I Atlas did indeed form in the thick disk, the implications are staggering because it means this object is incredibly old, potentially as much as 7 to 10 billion years old, which would make it nearly twice as old as our entire solar system, and older than Earth, by a factor of 2 or more. And it would mean this comet has been wandering through interstellar space since an epoch when the universe looked very different, when the Milky Way was still actively forming its current structure, when the sun and planets hadn't even been born yet, when the gas cloud that would eventually collapse to form our solar system was still just scattered atoms drifting in space. To put this age into perspective that humans can actually grasp, imagine that the entire history of the universe is compressed into a single calendar year, with the Big Bang happening at the stroke of midnight on January 1st. And in this cosmic calendar, the Milky Way galaxy begins to form sometime in mid-January. And by late February or early March, the thick disk population of stars is forming, And if 3I Atlas originated around one of those ancient thick disk stars, it would have formed sometime in March or April on this cosmic calendar, while our solar system wouldn't form until early September, meaning 3I Atlas spent the equivalent of 5 or 6 cosmic months drifting through space before our sun even existed, and Earth wouldn't form until September 8th, and the first simple life wouldn't emerge on Earth until late September, and dinosaurs wouldn't appear until mid-December, and modern humans wouldn't show up until the final hour of December 31st, and all of recorded human history would happen in the last few seconds before midnight. Researchers use sophisticated computer simulations to backtrack the trajectory of 3 Atlas through the galaxy, accounting for the gravitational influence of the Milky Way's overall structure, including the central bulge, the spiral arms, and the dark matter halo that surrounds everything. And they managed to trace the comet's path backward in time for about 10 million years, which sounds like a lot, but is actually just a tiny fraction of the object's potential total age, like rewinding a movie of your entire life, but only going back to last Tuesday. During those 10 million years, the simulations identified 93 different stars that 3I Atlas would have passed relatively close to, where relatively close in this context means within a few light years. And for each of those stars, the researchers calculated how close the encounter would have been, and whether the star's gravity could have significantly altered the comet's trajectory. And what they found was that none of those 93 encounters were close enough to matter. The closest approach to any star during that 10 million year period was about 0.3 light years, which equals roughly 63,000 astronomical units. And to put that in perspective, Pluto orbits the Sun at an average distance of about 40 astronomical units. So even the closest stellar encounter that 3I Atlas experienced in the past 10 million years was more than 1,500 times farther than Pluto is from the Sun. And at that distance, the gravitational influence would be negligible, not enough to capture the comet into orbit, or to significantly deflect its path, or to accelerate it or slow it down by any meaningful amount. Another team of researchers, led by Xavier Perez Cudo, a postgraduate student at Universidad da Coruña in Spain, conducted a similar but slightly different analysis that looked back 4.27 million years instead of 10 million. And they used data from the European Space Agency's Gaia Space Telescope, which spent years precisely measuring the positions, distances, and motions of more than 1 billion stars in the Milky Way, creating the most detailed three-dimensional map of our galaxy ever made. Using that Gaia data, the Perez-Cuto team identified 62 stars that 3I Atlas likely encountered over the past 4 million years, and they ran detailed calculations to see if any of those encounters could explain the comet's current trajectory and velocity, and their conclusion was definitive. None of the stars in the solar neighborhood can explain the trajectory and high velocity of 3I Atlas, which means this object didn't originate anywhere near us, and it must have come from farther away in the galaxy, from a region with very different properties than our local neighborhood. The team suggested that 3I Atlas most likely originates from the border region between the thin disk and the thick disk, a transition zone where the younger metal-rich stars of the thin disk give way to the older metal-poor stars of the thick disk. And this frontier region is particularly interesting from a scientific standpoint because it represents a snapshot of the galaxy during a transitional period in its history, when the violent early epoch of galaxy formation was winding down and the more settled era of regular star formation was ramping up. If the comet formed in this border region, it could potentially be even older than 7 billion years, possibly as old as 10 billion years, which would make it more than twice the age of our sun, and old enough that it could have formed around one of the very first generation of stars to emerge in this region of the galaxy after the initial burst of star formation that created the thick disk population. The idea that 3I Atlas could be 10 billion years old is almost incomprehensible, because that's such a vast span of time that nothing in human experience can adequately compare to it. And if this comet really is that ancient, then the star system where it formed is almost certainly long dead, because stars don't live forever. They burn through their nuclear fuel and eventually die, and the timescale for that process depends on the star's mass, with smaller stars living for hundreds of billions of years, but larger stars burning out in just a few million years, and sun-like stars living for about 10 billion years, before expanding into red giants and then collapsing into white dwarfs. This means that if 3I Atlas formed around a sun-like star 10 billion years ago, that star would be nearing the end of its life right now, possibly having already swelled into a red giant that swallowed up its inner planets. Or it might have already died and collapsed into a white dwarf, a dense stellar remnant about the size of Earth, but with the mass of the sun, slowly cooling and fading into darkness over trillions of years, and all the planets that once orbited that star, all the asteroids and comets and moons that made up that ancient solar system, would either have been destroyed when the star expanded, or would have been flung out into interstellar space, just like 3I Atlas was, scattered across the galaxy like dandelion seeds on the wind. Scientists believe that 3I Atlas was ejected from its home star system through a process that's actually quite common in planetary systems, especially in their early chaotic years, when large planets are still migrating inward and outward through gravitational interactions with each other, and with the remaining debris disk of gas and dust left over from star formation. When a comet or asteroid has a close gravitational encounter with a large planet like Jupiter or Saturn, it can get flung onto a new trajectory with a much higher velocity. And if the encounter is violent enough and the geometry is just right, that velocity can exceed the escape velocity of the star system, sending the object flying off into interstellar space, where it will wander for millions or billions of years until it randomly passes through another star system, if it ever does at all. The thick disk origin of 3I Atlas would also explain some of the unusual chemical properties that astronomers have detected in the comet, because if it formed around an old metal-poor star in the thick disk, then the protoplanetary disk of gas and dust from which it condensed would have had a very different composition than the disk that formed our solar system, with less carbon, less oxygen, less nitrogen, and less of all the other heavy elements that were produced by previous generations of stars. And those differences in composition could lead to different types of ices and minerals forming in the comet, different ratios of water ice to carbon dioxide ice, different amounts of organic compounds, different trace elements, and basically a chemical fingerprint that reflects the ancient galactic environment where it formed. One of the predictions made by the Oxford team, based on the thick disk origin hypothesis, is that 3I Atlas should be rich in water ice, because even though thick disk stars are metal-poor overall, they still have enough oxygen to form water molecules, and in the cold outer regions of a protoplanetary disk, that water would freeze into ice and get incorporated into comets and icy planetesimals. So when 3I Atlas gets close enough to the sun to start sublimating, we should see a lot of water vapor being released, and indeed, observations made in late September 2025 confirmed that the comet was releasing water vapor at an unexpectedly high rate, about the equivalent of a fire hose running at full blast, which matched the prediction and provided supporting evidence for the thick disk origin theory. The fact that we're getting to observe an object from the thick disk up close is scientifically invaluable, because even though the thick disk contains billions of stars, it's much harder to study than the thin disk, simply because the thick disk objects are farther away on average and more spread out. So getting detailed observations of individual thick disk stars requires large telescopes and long exposure times, and getting observations of planets or comets from thick disk systems has been completely impossible until now, because those objects are too small and too faint to see from Earth, even with our most powerful instruments. 3I Atlas represents a unique opportunity to study pristine material from the early galaxy, material that has been preserved in the deep freeze of space for billions of years without being heated or altered or contaminated by later events, like opening a time capsule that was sealed shut long before Earth existed. And the information encoded in that material could tell us things we can't learn any other way about what the galaxy was like in its youth. What kinds of chemical processes were happening around ancient stars, how planet formation might have differed in the early galaxy compared to more recent times, whether the basic building blocks of life, like water and organic molecules, were present in the same proportions back then, and potentially even whether the conditions that led to life on Earth were unique to our particular time and place, or whether they might have been common throughout galactic history. Chris Lintott, a professor at the University of Oxford and presenter of the BBC's The Sky at Night, captured the significance perfectly when he said this is an object from a part of the galaxy we've never seen up close before. And that statement really drives home how rare and precious this opportunity is. Because even though we can point our telescopes at the thick disk and count stars and measure their properties from a distance, we've never been able to hold a piece of thick disk material in our hands or study it with the kind of detailed instruments we can bring to bear on objects that pass through our solar system. And 3i Atlas is giving us that chance for the first time in human history. The age estimate of 7 to 10 billion years is based on the assumption that the comet originated in the thick disk population. But it's important to note that there's still significant uncertainty in that calculation because we can only trace the trajectory back a few million years with any confidence. And beyond that, the uncertainties multiply rapidly because we don't know exactly where every star in the galaxy was positioned millions of years ago. And we don't know the precise distribution of dark matter, which exerts gravitational influence on everything, but can't be directly observed. And we don't know every gravitational interaction that 3i Atlas might have experienced with giant molecular clouds or spiral density waves or any of the other massive structures that populate the galaxy and can nudge objects onto different paths. Some researchers have suggested that 3i Atlas might not be quite as old as 10 billion years, that it could have formed more recently around a thick disk star that itself is very old, but that formed a planetary system later in its life. Perhaps after capturing material from a passing gas cloud, or after a gravitational interaction with another star, triggered a new phase of planet formation. And in that scenario, the comet might be only a few billion years old, rather than 10 billion. But it would still be older than our solar system, and still represent material from a very different galactic environment. Other researchers have proposed that the high velocity of 3i Atlas might not be entirely explained by ejection from a planetary system, that the comet might have gotten an additional boost from some other mechanism, perhaps a close encounter with a massive star that accelerated it through gravitational slingshot effects. Or perhaps it passed through a dense stellar cluster where multiple gravitational interactions kicked it to higher and higher speeds over time. Or perhaps it was originally part of a binary comet system that broke apart, with each piece flying off in opposite directions and gaining velocity from the separation, similar to how a hammer thrower spins around and then releases the hammer, which flies away at high speed. The mystery of 3i Atlas's origin is far from solved, and it may never be completely solved, because the object has been traveling for so long through such a vast and complex environment that tracing it all the way back to its birthplace is probably impossible with current technology and current knowledge of the galaxy's structure. But every observation we make brings us closer to understanding where this ancient wanderer came from, and every spectrum we capture reveals a little more about the chemical composition that reflects its formation environment, and every measurement of its trajectory helps refine our models of how objects move through the galaxy over vast timescales. And all of this knowledge accumulates into a bigger picture of how galaxies work, how planetary systems form and evolve, how material gets recycled through the cosmos over billions of years, and ultimately, how rare or common our own existence might be in the grand scheme of cosmic history. The really mind-bending part of the 3I Atlas story begins when astronomers started pointing their most sophisticated instruments at this interstellar visitor and analyzing exactly what it's made of, because what they found challenged fundamental assumptions about how comets are supposed to behave and revealed chemical signatures that seem completely backwards compared to everything we've learned from studying comets in our own solar system. The first major clue that something unusual was happening came from observations made by NASA's Transiting Exoplanet Survey satellite, better known as TESS, which normally spends its time hunting for planets around distant stars, but just happened to be looking in the right direction between May 7th and June 3rd, 2025, when 3I Atlas was still way out beyond Jupiter's orbit, at more than 5 astronomical units from the Sun. TESS wasn't designed to study comets. It was designed to detect the tiny dips in a star's brightness that occur when a planet passes in front of it, but it's also extremely sensitive to changes in brightness of any object in its field of view. And when astronomers went back through the TESS data after 3I Atlas was officially discovered, they found something that shouldn't have been there, which was a dramatic brightening of the comet over the course of that 1-month observation period. Now, you have to understand that at 5 astronomical units from the Sun, space is incredibly cold, cold enough that most comets remain completely frozen and inactive because the Sun's heat isn't strong enough to sublimate the ices that make up their surface, and sublimation is the technical term for when a solid material transitions directly into a gas without passing through a liquid phase, which is what happens in the vacuum of space, where liquid can't exist. Most comets from our solar system don't start becoming active until they get inside about 3 to 4 astronomical units from the Sun, which is roughly the distance of the asteroid belt between Mars and Jupiter. And that's because typical solar system comets are primarily made of water ice, which is extremely stable and requires a lot of energy to sublimate, needing temperatures well above -170 degrees Celsius before the sublimation process really kicks into high gear. When TESS observed 3I Atlas traveling from about 5.5 astronomical units to 4.5 astronomical units over that 1-month period, astronomers calculated that the object should have gotten brighter by a factor of about 1.5, which would have been caused by the simple fact that it was getting closer to the Sun and therefore reflecting more sunlight back toward Earth. But what they actually measured was a brightness increase by a factor of 5, which was more than 3 times higher than expected. That massive excess brightness could only mean one thing, which was that 3I Atlas was already forming a coma, that fuzzy cloud of gas and dust that surrounds an active comet, and it was forming that coma way farther from the Sun than any normal comet should. And this immediately told scientists that 3I Atlas wasn't made of the same stuff as solar system comets, or at least not in the same proportions. The mystery deepened when astronomers started measuring the polarization of light reflected from the comet, because polarization is a property of light that describes the orientation of the light waves, and when light bounces off dust particles or ice crystals in space, the way it scatters depends on the size, shape, and composition of those particles. So by measuring how polarized the reflected light is, you can learn about the material doing the reflecting. Most objects in space, including pretty much every comet and asteroid we've studied from our solar system, show what's called positive polarization, which means that when light from the Sun hits the dust and gas around the object, it preferentially scatters perpendicular to the direction it came from, bouncing off to the sides rather than straight back toward the Sun. And the degree of positive polarization can tell you whether the dust particles are small or large, fluffy or compact, icy or rocky. 3I Atlas completely violated this pattern, because when astronomers measured its polarization using telescopes in Chile and Spain and other locations around the world, they found that the comet showed negative polarization, meaning light was bouncing straight back toward the Sun rather than scattering to the sides. And not only was it negative, it was the most extremely negative polarization ever measured for any object in our solar system or any interstellar visitor we've encountered. The previous record holder for extreme negative polarization was asteroid 1704, Watchman, which is a weird near-Earth asteroid that crosses Mars's orbit and has some unusual properties. But 3I Atlas blew right past that record, showing polarization values that were off the charts and indicating that the dust particles in its coma have a size distribution and composition that's fundamentally different from what we're used to seeing. Scientists believe the extreme negative polarization is caused by the presence of very large dust grains in the coma, particles that are several micrometers in radius, which is much larger than the typical submicron-sized dust particles found in most comets. And these large grains would scatter light differently than small grains, producing the negative polarization signature that was observed. The large grain size also suggests that the material sublimating from 3I Atlas's surface is being ejected gently rather than explosively, which would be consistent with sublimation driven by carbon dioxide rather than water, because carbon dioxide sublimation is a much more gradual process that can carry larger particles along with the gas flow, whereas water sublimation tends to be more violent and energetic, shattering particles into smaller fragments. The real breakthrough in understanding 3I Atlas's composition came in August 2025, when NASA's James Webb Space Telescope, the most powerful space telescope ever built, turned its attention to the comet and captured near-infrared spectroscopy data that revealed exactly what gases were present in the coma. Spectroscopy is essentially like taking a chemical fingerprint because different molecules absorb and emit light at very specific wavelengths, and by spreading out the light from an object into a spectrum and looking for which wavelengths are missing or enhanced, you can identify exactly what molecules are present and even measure how abundant they are. The James Webb observations, which were announced by NASA on August 25, 2025, showed something that astronomers had suspected but never seen so definitively in an interstellar object, which was that 3I Atlas's coma was absolutely dominated by carbon dioxide gas, with the ratio of carbon dioxide to water being approximately 8:1, which is completely inverted compared to typical solar system comets. To put that in perspective, when you study comets from the Oort cloud or the Kuiper belt, which are the regions beyond Neptune where most long-period comets come from, you typically find that they're mostly water ice with small amounts of carbon dioxide, carbon monoxide, methane, ammonia, and other volatiles mixed in. And a typical ratio might be something like 10 parts water to 1 part carbon dioxide. So 3I Atlas has basically the opposite ratio, 8 parts carbon dioxide to 1 part water, making it one of the most carbon dioxide-rich comets ever observed. The James Webb data also detected smaller amounts of carbon monoxide gas and carbonyl sulfide gas in the coma, both of which are interesting molecules in their own right, because carbonyl sulfide contains sulfur, which is a key element for organic chemistry and for the formation of certain types of biological molecules. And carbon monoxide is important because it tells you about the temperature and chemistry of the region where the comet formed. Even more remarkably, the James Webb Telescope was able to detect the presence of heavy carbon dioxide molecules containing the isotope carbon-13, instead of the more common carbon-12. And isotopes are versions of an element that have different numbers of neutrons in their nucleus. So carbon-12 has 6 protons and 6 neutrons, while carbon-13 has 6 protons and 7 neutrons. And the ratio of carbon-13 to carbon-12 in a material can tell you about the conditions under which that material formed, including the temperature and the sources of carbon that were available. Unfortunately, the carbon-13 signal was partially obscured by dust and other gases in the coma, so astronomers couldn't get an accurate measurement of the isotope ratio. But just detecting carbon-13 at all is significant because it means the heavy isotope is present in measurable amounts. and future observations might be able to pin down the exact ratio, which could reveal whether 3I Atlas formed in an environment similar to our solar system or in a radically different setting. The high carbon dioxide to water ratio immediately explained why 3I Atlas started forming a coma so early, way out at 5 astronomical units, because carbon dioxide ice sublimates at much lower temperatures than water ice. And if you've ever seen dry ice, which is frozen carbon dioxide, you know that it starts smoking and sublimating almost immediately when you take it out of the freezer and expose it to room temperature air, whereas regular water ice just sits there and slowly melts into a puddle. In space, carbon dioxide ice becomes unstable and starts sublimating at temperatures around -123 degrees Celsius, which occurs at distances of about 5 to 6 astronomical units from a sun-like star. But water ice doesn't really start sublimating vigorously until temperatures rise above -100 degrees Celsius, which doesn't happen until you get inside about 3 astronomical units. So 3I Atlas, being made primarily of carbon dioxide ice, started its sublimation process much earlier than a water ice comet would, and that's why tests detected it brightening and forming a coma when it was still way out beyond Jupiter. The carbon dioxide-dominated composition also raised fascinating questions about where and how 3I Atlas formed. Because in our solar system, the distribution of ices in the protoplanetary disk that eventually formed the planets was controlled by something called frost lines or snow lines, which are specific distances from the young sun, where different volatile compounds would freeze out of the gas phase and condense into solid ices. The water frost line in our solar system was located at about 2.7 astronomical units, roughly where the asteroid belt is today. And beyond that line, water could condense into ice, which is why the asteroids in the outer belt and the moons of Jupiter and Saturn are so rich in water ice. The carbon dioxide frost line was located much farther out, somewhere around 10 to 15 astronomical units, depending on the exact conditions in the early solar system. And beyond that line, carbon dioxide could condense into ice and get incorporated into comets and icy bodies. The fact that 3I Atlas is so rich in carbon dioxide suggests that it formed beyond the carbon dioxide frost line in its home star system, far from its parent star in a very cold region, where carbon dioxide ice was more abundant than water ice. And that in turn tells us something about the architecture of that distant planetary system, suggesting it may have had a very different structure than our own, with the giant planets located at different distances, or with a different distribution of material in the protoplanetary disk. As 3I Atlas continued its journey toward the Sun through the late summer and early fall of 2025, astronomers kept monitoring its chemical output, and they started to see dramatic changes in what was being released from the surface. By late September, when the comet had passed inside Mars's orbit and was approaching 2 astronomical units from the Sun, the production of water vapor suddenly spiked, increasing to about 250 kilograms per second, which is roughly equivalent to a fire hose running at full blast. And this was way more water than astronomers expected to see at that distance. The ratio of carbon dioxide to water, which had been 8-to-1 back in the summer, started to flip as the water ice on the comet's surface began to sublimate vigorously, and by early October, the ratio was closer to 1-to-1, showing that as the comet got hotter, different layers of material were being exposed, and different ices were starting to dominate the outgassing. This layered structure makes sense if you think about how comets form and evolve, because when a comet is far from any star and drifting through the cold of interstellar space, the outer layers get bombarded by cosmic rays and ultraviolet radiation, which can alter the chemistry and create a hardened crust on the surface. And then when the comet finally gets close to a star, that outer crust sublimates first, releasing whatever volatiles were trapped in it, and then deeper layers with different compositions get exposed and start sublimating. Another bizarre chemical signature detected in 3I Atlas was the presence of metals in the coma, specifically nickel and iron, which are elements you don't normally associate with the fluffy, icy composition of a comet. And when astronomers first detected nickel in the coma, back in the summer, using ultraviolet spectroscopy from ground-based telescopes, they were puzzled because metals require extremely high temperatures to sublimate, temperatures that shouldn't exist anywhere near a comet that's still several astronomical units from the sun. Nickel and iron are both common elements in the universe because they're produced in the cores of massive stars during the final stages of nuclear fusion, before those stars explode as supernovas, and the blast from the supernova scatters these metals out into space, where they get incorporated into the next generation of stars and planets. So finding metals in comets isn't surprising in principle, because comets form from the same primordial material that makes up everything else in a planetary system. What was surprising about the nickel detection in Three-Eyed Atlas was the ratio of nickel to iron, because normally these two metals are found together in roughly solar proportions, meaning the ratio of iron to nickel is about 17:1, since iron is much more abundant in the universe than nickel. But the early observations of Three-Eyed Atlas showed lots of nickel, but essentially no iron, which is backwards, and suggests some kind of chemical fractionation process separated these elements in the material that formed the comet. Several theories have been proposed to explain the missing iron, with one idea being that the iron is locked up in minerals or compounds that don't sublimate as easily as nickel compounds, so the nickel gets released preferentially when the comet starts out gassing, and another theory suggesting that the parent star system, where Three-Eyed Atlas formed, had an unusual abundance pattern, with more nickel relative to iron than our sun has, which could happen if that star formed from gas that had been enriched by specific types of supernova explosions that produce more nickel. The mystery of the missing iron resolved itself somewhat in late September, when astronomers using more sensitive instruments started detecting iron emission lines in the spectrum of Three-Eyed Atlas. And over the course of just a few weeks, the ratio of nickel to iron shifted toward more normal values, suggesting that as the comet got closer to the sun and hotter, deeper layers of material were being exposed that contained both metals in more typical proportions, and whatever process had separated the nickel from the iron in the outer layers didn't extend all the way through the comet's interior. The presence of metals in the coma, regardless of their ratios, is significant because it provides clues about what happened to this comet during its billions of years wandering through interstellar space, because cosmic rays, which are high-energy particles that fill the galaxy and can penetrate deep into solid objects, can alter the chemistry of surface materials over long timescales, breaking apart molecules, creating new compounds, and potentially concentrating certain elements in surface layers. A research team, led by scientists at the University of Cambridge, published a fascinating paper in late October 2025, in which they used computer simulations to model what would happen to a comet's surface chemistry after 1 billion years of exposure to galactic cosmic rays. And their results showed that cosmic ray bombardment can create a thick, irradiated crust on a comet's surface that has completely different properties than the pristine ice underneath, with the crust being enriched in certain organic compounds, depleted in others, and potentially having different abundances of trace elements, like metals. The Cambridge team suggested that the weird chemistry we're seeing in Three-Eyed Atlas might not represent the original composition of its parent star system at all, but rather might be the result of billions of years of cosmic ray weathering that has transformed the outer layers into something that no longer resembles the pristine material from which it formed, which means that to really understand where this comet came from and what its home system was like, we need to somehow get through that irradiated crust to the unaltered material underneath, which will happen naturally as the comet sublimates and sheds its outer layers. But we need to observe it carefully during that process to distinguish between the altered and unaltered material. Spectroscopic observations using ground-based telescopes in South Africa and Spain revealed another interesting property of Three-Eyed Atlas, which is that the dust in its coma shows a reddish color with a spectral slope of 22.8% per micrometer, meaning that as you look at longer and longer wavelengths of light in the optical range from 400 nanometers in the blue to 700 nanometers in the red, the comet reflects more and more light, making it appear distinctly reddish rather than gray or bluish. This reddish color is similar to what we see in D-type asteroids, which are primitive asteroids found in the outer solar system that are thought to contain a lot of organic material and carbon-rich compounds. And it's also similar to the color of 2I Borisov, the previous interstellar comet, which showed a reddish hue, indicating the presence of organic compounds in its coma. The reddish color is believed to be caused by organic molecules called tholins, which are complex carbon-based compounds that form when simpler molecules like methane, ethane, and nitrogen are exposed to ultraviolet radiation or cosmic rays over long periods of time. And tholins are responsible for the orange color of Titan's atmosphere, the reddish patches on Pluto's surface, and the colors of many objects in the Kuiper belt. So finding them in 3I Atlas suggests that this interstellar comet went through similar chemical processing during its long journey through space. The James Webb telescope also detected water ice in the coma of 3I Atlas, not just water vapor, but actual tiny ice crystals that were still solid despite being in the vacuum of space and exposed to sunlight. And analysis of the infrared spectrum indicated that these ice grains are smaller than 1 micrometer in diameter, which is extremely small, about 1/100th the width of a human hair, and the water ice appears to be in the amorphous form rather than the crystalline form, though the data wasn't definitive enough to rule out crystalline ice entirely. Amorphous ice is a disordered form of solid water, where the molecules are arranged randomly, rather than in the neat geometric lattice structure of crystalline ice. And amorphous ice forms when water vapor freezes very rapidly at extremely cold temperatures, typically below -160 degrees Celsius, which is exactly the kind of environment you'd expect in the outer regions of a protoplanetary disk or in interstellar space. So finding amorphous ice in 3I Atlas is consistent with the comet forming in a very cold environment and never being heated enough during its lifetime to convert that amorphous ice to the crystalline form. Additional ultraviolet spectroscopy from ground-based telescopes detected cyanide molecules in the coma, specifically the CN radical, which is a fragment of hydrogen cyanide that forms when UV light from the sun breaks apart the parent molecules. And while cyanide might sound scary because of its association with poisons, it's actually extremely common in comets and is one of the key building blocks for more complex organic molecules, including amino acids, which are the building blocks of proteins. The combination of all these chemical signatures, the high carbon dioxide to water ratio, the extreme negative polarization, suggesting large dust grains, the reddish color indicating organic compounds, the presence of metals in unusual ratios, the amorphous water ice, and the detection of carbon-bearing molecules like cyanide and carbonyl sulfide paints a picture of an object that formed in a very different environment than anything in our solar system, and that has been profoundly altered by billions of years of exposure to the harsh radiation environment of interstellar space, creating a chemical time capsule that's both alien and familiar, containing the same basic elements and compounds we see in solar system comets, but mixed in different proportions and processed by different mechanisms, and every spectrum we capture and every molecule we identify brings us one step closer to understanding the incredible diversity of planetary systems across our galaxy and the range of conditions under which icy bodies can form and survive. One of the most baffling aspects of 3I Atlas that had astronomers scratching their heads and checking their instruments to make sure they weren't seeing things wrong was the bizarre behavior of the comet's tail, or more accurately, the complete absence of a proper tail during the early months of observation, followed by the appearance of a feature that pointed in the exact opposite direction from where any comet tail should naturally point, which violated one of the most fundamental and reliable rules about how comets are supposed to behave when they get close to the sun. To understand why this was so shocking, you need to understand what a comet tail actually is and what creates it. Because despite what many people assume, a comet's tail isn't like the exhaust trail from a rocket or airplane that shows you which direction the object came from. Instead, a comet's tail always points away from the sun, regardless of which direction the comet is actually traveling. And this happens because of something called solar wind and radiation pressure. The sun isn't just sitting there passively radiating light and heat. It's constantly blasting out a stream of charged particles called the solar wind, which consists of electrons and protons that get accelerated to incredible speeds by the intense heat and magnetic activity in the sun's outer atmosphere. And this wind flows outward in all directions at speeds of about 400 to 700 kilometers per second, creating an invisible bubble around the sun called the heliosphere that extends well beyond the orbits of all the planets. When a comet gets close enough to the sun for its surface ices to start sublimating, all that gas and dust being released from the nucleus doesn't just hang around in a static cloud. It gets caught by the solar wind and pushed away from the sun, and the lighter particles, especially dust grains smaller than a micrometer and gas molecules, get blown back to form the characteristic tail that we associate with comets. And that tail always points directly away from the sun, like a windsock points away from the wind. There's also radiation pressure to consider, which is the physical push that light itself exerts on objects. And even though individual photons of light are essentially massless, when trillions upon trillions of them hit something per second, they exert a measurable force. And for very small dust particles in space, radiation pressure from sunlight can actually be strong enough to overcome gravity and push those particles away from the sun, contributing to the formation of the tail alongside the solar wind. So based on everything we know about comet physics, from centuries of observations, when 3I Atlas started forming a coma in the summer of 2025, as it passed through Jupiter's orbit, and the sun's radiation began sublimating the carbon dioxide ice on its surface, we expected to see a tail developing that pointed away from the sun in the anti-solar direction, but that's not what happened at all. The first detailed images of 3I Atlas, captured by ground-based telescopes in July 2025, showed something that made absolutely no sense, which was a coma that appeared elongated, not in the anti-solar direction, but in the sunward direction, meaning the brightest and most extended part of the fuzzy cloud surrounding the comet's nucleus was pointing toward the sun rather than away from it, creating what initially looked like a tail, pointing in the completely wrong direction. Astronomers using telescopes in the southern hemisphere, particularly the Very Large Telescope in Chile, which is actually an array of 4 separate 8.2-meter telescopes that can work together or independently, captured a series of images through July and August that clearly showed this sun-facing feature. And at first, many researchers assumed this must be some kind of observational artifact, maybe an error in how the images were processed, or some weird effect of the telescope optics, or atmospheric distortion. But multiple independent observations from different telescopes in different locations all showed the same thing: a distinct elongation of the coma toward the sun. The feature was particularly prominent in images taken on July 21st by the Hubble Space Telescope, which has the advantage of being above Earth's atmosphere and therefore can capture incredibly sharp images without any blurring from atmospheric turbulence. And the Hubble images definitively confirmed that yes, 3I Atlas really was developing some kind of sun-facing structure. And no, it wasn't an instrumental error or an optical illusion. Scientists quickly realized that calling this feature a tail was technically incorrect because by definition, a comet's tail is formed by material being blown away from the nucleus by solar wind and radiation pressure, and something pointing toward the sun couldn't be formed by that mechanism, since wind and radiation pressure push things away from the sun, not toward it. So they started calling it a sun-facing plume, or a sunward jet instead of a tail, which more accurately described what was actually happening. The leading theory to explain this bizarre sun-facing plume involves the early and vigorous sublimation of carbon dioxide ice from 3 Atlas's nucleus. Because remember, this comet is dominated by carbon dioxide rather than water ice, and carbon dioxide starts sublimating at much lower temperatures and much greater distances from the sun than water does. So 3I Atlas began actively outgassing when it was still more than 5 astronomical units away, way out beyond Jupiter, where the solar wind is relatively weak because it spreads out and dilutes as it travels farther from the sun, following an inverse square law where doubling the distance reduces the wind pressure by a factor of 4. At those extreme distances, the solar wind pressure wasn't strong enough to immediately blow away all the gas and dust being released from the comet's surface. So instead of forming a tail that streamed away from the nucleus, the sublimating material accumulated on the sunward side of the nucleus, because that's the side being heated by sunlight, and therefore the side where sublimation was happening most vigorously, creating a bright plume of gas and dust that extended out in front of the comet as it moved through space. You can think of it like steam rising from a pot of boiling water. The steam goes up initially, because that's where the heat is coming from at the bottom of the pot, and only later does the steam get caught by air currents in the room and blown in whatever direction the air is moving. And similarly, the gas and dust coming off 3 Atlas initially just expanded outward from the heated sunward face of the nucleus before eventually getting caught by the solar wind and redirected into an anti-solar direction. Another factor that contributed to the sun-facing plume was the comet's direction of motion, because 3 Atlas was traveling almost directly toward the sun during July and August as it fell deeper into the inner solar system. So the sunward side of the nucleus was also the forward-facing side in terms of the comet's velocity, and as gas and dust sublimated from that surface, it carried forward momentum from the rotation and motion of the nucleus itself, causing the material to shoot out ahead of the comet, like water spraying from a rotating lawn sprinkler. Images taken by Austrian astrophotographer Michael Jaeger, who operates a private observatory equipped with high-quality telescopes and has become famous for capturing detailed images of comets, clearly showed this fan-shaped structure extending from the inner coma of 3I Atlas toward the sun, and his images from late August 2025 revealed that the sunward plume had a complex structure with multiple bright jets or filaments, suggesting that sublimation wasn't happening uniformly across the entire sunward face of the nucleus, but was instead concentrated in specific active regions where the ice was particularly volatile, or where cracks and fissures in the surface allowed gas to escape more easily. By late August, something fascinating started to happen, which was that 3I Atlas finally began developing what looked like a proper anti-solar tail pointing away from the sun. And this happened because as the comet continued moving closer to the sun, the solar wind strength increased and radiation pressure became strong enough to overcome the outward expansion of gas and dust from the nucleus and start pushing that material back in the anti-solar direction. So for a brief period, 3I Atlas displayed both features simultaneously, with the sunward plume still visible in the inner coma, close to the nucleus, where freshly sublimated material was still expanding outward before getting caught by the wind, and a faint anti-solar tail extending outward from the nucleus in the opposite direction, where material that had already been processed by the solar wind was streaming away. The first confirmed observations of the anti-solar tail came from the Gemini South Telescope, another 8.2-meter telescope located in Chile, which captured images on August 27th showing a distinct tail extending about 30 arcseconds in angular length away from the Sun. And when astronomers converted that angular measurement into actual physical distance, accounting for how far away 3I Atlas was at the time, they calculated the tail was about 56,000 kilometers long, which is roughly 4.5 times the diameter of Earth, making it a pretty substantial structure, though nowhere near as impressive as the tails of famous great comets like Hale-Bopp or Hyakutake, which had tails extending millions or even tens of millions of kilometers. By mid-September, the anti-solar tail had grown to about 50 arcseconds in angular length, corresponding to roughly 100,000 kilometers in actual physical size, and the tail was becoming more and more prominent in images as the comet's activity increased with its approach to perihelion. And by this point, the sunward plume had faded significantly, not because sublimation had stopped, but because the solar wind was now strong enough to immediately blow away the gas and dust as soon as it left the nucleus, so the material didn't have time to accumulate in a visible plume before being swept back into the tail. The morphology of the anti-solar tail, meaning its shape and structure, revealed additional information about what was happening on the comet's surface and what kind of material was being ejected, because comet tails aren't uniform structures. They typically consist of two distinct components called the dust tail and the ion tail, or plasma tail, and these two components behave differently and appear different in images. The dust tail is made of solid particles, tiny grains of rocky material, and carbonaceous compounds, ranging from submicron sizes up to particles several micrometers in diameter, and these particles are heavy enough that they don't get blown perfectly straight back by the solar wind. Instead, they follow curved trajectories as they're pushed away from the nucleus, while also maintaining some of the comet's orbital motion, creating a broad curved dust tail that fans out behind the comet and typically appears yellowish or white in color because the dust particles reflect sunlight. The ion tail is made of ionized gas molecules, atoms that have been stripped of one or more electrons by ultraviolet radiation from the sun, and these ions are electrically charged, so they interact strongly with the sun's magnetic field, which is carried along by the solar wind, and the magnetic field channels the ions into a narrow straight tail that points exactly away from the sun. And because certain ions, like carbon monoxide plus and carbon dioxide plus, emit light at specific wavelengths when they're excited by solar radiation, the ion tail often appears bluish in color and sometimes shows a lot of fine structure with knots and streamers and disconnection events where chunks of the tail break off and drift away. Observations of 3I Atlas through September and October showed that its anti-solar tail was primarily a dust tail with a broad fan-shaped structure and no obvious ion tail component, which was somewhat surprising given the high levels of carbon dioxide and carbon monoxide detected in the coma, both of which should produce strong ion tails when ionized by solar ultraviolet radiation, and the absence or weakness of the ion tail could indicate that the magnetic field structure around the comet wasn't conducive to channeling ions into a straight tail, or it could mean that the dust production was so high that the dust tail simply outshone any ion tail that might have been present, or there might have been some other factor related to the comet's chemistry or the solar wind conditions at the time that suppressed ion tail formation. The length and brightness of 3I Atlas's tail remained relatively modest compared to famous comets of the past, and this was partly because the comet's perihelion distance was 1.36 astronomical units, which put it slightly farther from the Sun than Earth's orbit, and considerably farther than comets like Hale-Bopp, which passed within 0.914 astronomical units, or about 85 million miles, meaning Hale-Bopp got almost 140 million miles closer to the Sun than 3I Atlas did, and that extra distance made a huge difference in terms of how much heating occurred and how much sublimation happened, and how dramatic the tail became. Comet tails are essentially controlled by two factors: the rate of sublimation, which determines how much material is available to form the tail, and the strength of the solar wind and radiation pressure, which determines how fast that material gets blown away and how extended the tail becomes. And both of these factors increase dramatically as you get closer to the sun. So a comet passing at 0.5 astronomical units is going to develop a much more spectacular tail than a comet passing at 1.5 astronomical units, even if they're otherwise identical in size and composition. Theoretical models of comets predict that tail length should scale roughly with the square root of sublimation rate multiplied by the square root of time, which means doubling the sublimation rate only increases tail length by about 40% unless the comet maintains that high sublimation for a long time. And since 3I Atlas spent relatively little time at close approach to the sun, because it was moving so fast, it didn't have much time to develop an extremely long tail. What made the tail of 3I Atlas particularly interesting from a scientific standpoint wasn't so much its appearance, which was fairly typical for a moderately active comet at that distance from the sun, but rather the information the tail carried about, the comet's composition, and the processes happening on its surface. Because by analyzing the dust-to-gas ratio in the tail and the size distribution of dust particles and the spectral properties of the material, scientists could reconstruct what was happening on the nucleus and what layers were being exposed as the surface sublimated away. The dust-to-gas ratio is a key parameter that tells you how much solid material is being released relative to how much gas is being released. And for typical solar system comets, this ratio is usually somewhere around 1, meaning roughly equal masses of dust and gas. But observations of 3I Atlas suggested a higher dust-to-gas ratio, possibly as high as 2 or 3, indicating that the comet was releasing a lot of dust along with the gases, and this high dust production could explain why the anti-solar tail was so dominated by dust rather than showing a prominent ion component. As 3I Atlas passed through Perihelion on October 29, 2025, reaching its closest point to the sun at 1.36 astronomical units. The comet was unfortunately positioned almost directly behind the sun as seen from Earth, a geometric configuration called solar conjunction that happens when an object's orbit takes it to the far side of the sun from our perspective, and this meant that for several weeks around perihelion, we couldn't observe 3I Atlas at all because it was lost in the sun's glare. And this was incredibly frustrating for astronomers because perihelion is typically when comets are at their most active, when sublimation is happening at maximum rate, when tails are longest and brightest, when all the action is happening, and we couldn't see any of it. The comet began emerging from behind the sun in early November 2025, reappearing in the pre-dawn sky before sunrise, and astronomers eagerly pointed their telescopes at it to see what had changed during its close encounter with the sun. And what they found was both fascinating and puzzling, because 3I Atlas had definitely been affected by its passage through perihelion, but not necessarily in the ways they expected. Images captured on November 8th by Michael Yeager showed that the comet now possessed a clearly visible tail, confirming that the perihelion passage had indeed triggered increased activity, and the tail appeared to extend for at least several arc minutes in angular length, suggesting it had grown significantly longer than the roughly 100,000 kilometer tail observed in September, though detailed measurements were still being conducted to determine the exact physical length. What was puzzling was that some observations reported by theoretical physicist A.V. Loebi suggested that 3I Atlas appeared not to have a prominent tail after perihelion, instead showing up as more of a blob or compact coma without the extended streaming structure typical of an active comet tail. And this discrepancy between different observers' reports could be due to differences in observing conditions, differences in telescope sensitivity and resolution, differences in what wavelengths of light were being observed, or possibly even real changes in the comet's activity level happening over short timescales as different regions of the nucleus rotated in and out of sunlight. The behavior of 3I Atlas's tail, from the bizarre sun-facing plume in July and August to the development of a proper anti-solar dust tail in September and October to the uncertain state. After Perihelion in November tells a complex story about how an ancient interstellar comet responds to the sun's heat after billions of years in the frozen darkness of space. And it demonstrates that even though we think we understand how comets work based on studying thousands of solar system comets over hundreds of years, there's still so much we don't know, especially when we're dealing with objects from other star systems that formed under different conditions and have different compositions and behave in ways that surprise us. The trajectory of 3I Atlas through the inner solar system set up what would turn out to be one of the most fortunate cosmic coincidences in the history of planetary science, because on October 3, 2025, the comet passed within 0.19 astronomical units of Mars, which translates to about 28 million kilometers, or roughly 18 million miles, making Mars by far the closest planet to receive a visit from this ancient interstellar wanderer. And what made this encounter truly extraordinary wasn't just the proximity, but the fact that we currently have more active spacecraft at Mars than at any other planet besides Earth, with multiple orbiters circling the red planet, equipped with cameras and spectrometers that could potentially capture unprecedented close-up images and data from an interstellar object. Mars has become something of a hub for robotic exploration over the past 2 decades, with NASA operating 3 orbiters in Martian orbit, including the Mars Reconnaissance Orbiter, which launched in 2005 and carries the most powerful camera ever sent to another planet, an instrument called HiRES, which stands for High Resolution Imaging Science Experiment, and can resolve features as small as about 1 meter across on the Martian surface from its orbital altitude, making it capable of photographing not just landscapes and geological formations, but also the rovers and landers operating on the surface. And if pointed at 3I Atlas during the flyby, HiRES could potentially capture details of the comet's nucleus and inner coma that would be impossible to see from Earth-based telescopes. In addition to the American orbiter, the European Space Agency operates the Mars Express spacecraft, which has been circling Mars since 2003 and carries a suite of instruments, including high-resolution cameras and spectrometers, and the Trace Gas Orbiter, which arrived in orbit in 2016, specifically to study the Martian atmosphere and search for trace gases like methane that might indicate biological activity, though it could potentially be redirected to observe the comet as well. And then there's China's Tianwen-1 orbiter, which successfully entered Mars orbit in February 2021 as part of China's first independent interplanetary mission, and it carries cameras capable of imaging the comet from a relatively close vantage point. Down on the surface of Mars, we have NASA's Perseverance rover, which landed in Jezero crater in February 2021 and carries the most advanced suite of scientific instruments ever sent to another planet, including high-definition cameras designed primarily for studying rocks and soil, but potentially capable of photographing bright objects in the Martian sky. And while Perseverance's cameras aren't optimized for astronomy the way telescope cameras are, they could still capture valuable images of 3I Atlas that would show how bright the comet appeared from Mars, and whether any tail structure was visible from that vantage point. The Mars encounter was particularly valuable because it occurred at a time when Earth-based observations of 3I Atlas were becoming increasingly difficult due to the comet's position in the sky. Because as 3I Atlas continued moving inward toward its perihelion on October 29th, it was moving almost directly toward the Sun from Earth's perspective, which meant that the angular separation between the comet and the Sun, as seen from Earth, was shrinking day by day, and by early October, 3I Atlas was only about 20 to 30 degrees away from the Sun in the sky, which meant it could only be observed during a narrow window just after sunset or just before sunrise, when the sky was dark enough to see faint objects. But the comet was still above the horizon, and even then, the observations had to contend with atmospheric extinction and scattering from the Sun's light, which made it difficult to see fine details. Mars, being in a different location in its orbit around the Sun, had a much better viewing geometry for the October 3rd flyby, with 3I Atlas appearing much farther from the Sun in the Martian sky, and therefore being observable against a darker background without the interference of solar glare. And this favorable geometry, combined with the close approach distance, meant that Mars-based observations could potentially reveal details about the comet's structure and activity that would be invisible from Earth. The excitement in the astronomical community about the Mars flyby was palpable in the weeks leading up to October 3rd, with researchers and space enthusiasts eagerly anticipating the images that would hopefully be captured by the various spacecraft. And there was particular interest in whether the Mars Reconnaissance Orbiter's high-rise camera would be able to photograph the comet at high resolution, because if it could, those images would represent by far the closest and most detailed views of an interstellar object ever obtained, potentially revealing the shape and structure of the nucleus itself, rather than just the surrounding coma. However, coordinating observations from Mars orbiters is complicated because these spacecraft are on tight schedules, with observations planned months in advance, and their primary mission is to study Mars itself, rather than other objects in the solar system. So reprogramming them to observe a comet requires convincing mission planners that the observation is scientifically valuable enough to justify interrupting the normal observation schedule. And then there's the technical challenge of pointing the instruments at the right place at the right time, which is non-trivial when you're dealing with a fast-moving target millions of kilometers away. On October 3rd, as 3I Atlas made its closest approach to Mars, passing through the point of minimum separation at a precisely calculated time based on orbital mechanics, astronomers on Earth waited anxiously for data to start flowing back from the various Mars spacecraft. But there's always a time delay, because radio signals traveling at the speed of light take between 4 and 22 minutes to travel from Mars to Earth, depending on where the two planets are in their respective orbits. And on October 3rd, 2025, Mars was relatively close to Earth at about 1.3 astronomical units, or roughly 195 million kilometers, which meant the signal travel time was about 11 minutes each way. So even real-time observations had a 22-minute round-trip delay. The first images to be released publicly came not from the sophisticated orbiters, but from NASA's Perseverance rover operating on the Martian surface. And while these weren't the high-resolution close-ups that everyone was hoping for, they were still historically significant because they represented the first time a robotic spacecraft on the surface of another planet had photographed an interstellar object, and they showed how 3I Atlas appeared in the Martian night sky to an observer standing on the red planet's rust-colored surface. The Perseverance images captured on the night of October 3rd showed a bright fuzzy patch of light against the dark Martian sky. And because the rover's cameras weren't designed for astronomical observations and don't have the sensitivity of dedicated telescope cameras, the engineering team had to get creative with their imaging strategy, taking multiple 30-second long exposures that were then stacked together to accumulate enough light to make the comet visible. The stacking process, which is a common technique in astrophotography, where you take many identical exposures and digitally combine them to increase the signal-to-noise ratio and bring out faint details that would be invisible in any single exposure, resulted in images that showed 3I Atlas as a somewhat elongated blob of light, with the comet's motion across the sky during the multiple exposures, creating a slight streaking effect that made it look more like a dash or a line than a point source. But even with these limitations, the images clearly showed that 3I Atlas was visible from Mars and had a distinct coma, making it recognizable as a comet rather than just a star or planet. The European Space Agency's ExoMars Trace Gas Orbiter also successfully captured images of 3I Atlas during the October 3rd flyby, and these orbital observations provided a clearer view than Perseverance's surface-based images, because the orbiter was above the Martian atmosphere and therefore didn't have to contend with atmospheric scattering or dust that could blur the images, and the ExoMars images showed 3I Atlas as a more defined fuzzy object with what appeared to be a faint tail, or at least an elongated coma structure, extending in the anti-solar direction, confirming that by early October the comet had indeed developed a proper dust tail that was visible even from Mars's orbit. What was particularly tantalizing about the ExoMars images was that they showed structure in the inner coma close to where the nucleus would be located, with some brighter regions, suggesting asymmetric outgassing or jets of material being ejected from specific active regions on the nucleus surface. But the resolution wasn't quite high enough to resolve the nucleus itself as a distinct point separate from the surrounding coma. So while we could see that something interesting was happening in the inner coma, we couldn't yet see the actual solid body of the comet, which probably measured only a few kilometers across and would appear incredibly tiny even from a distance of 28 million kilometers. The big question on everyone's mind was whether NASA's Mars Reconnaissance Orbiter had successfully photographed 3I Atlas with its high-rise camera, because if it had, those images would potentially show unprecedented detail and might even resolve the nucleus as a separate object from the coma. And mission scientists had indicated that they were planning to attempt high-rise observations, but as of early November 2025, those images had not been publicly released, and there was growing speculation about why the delay was occurring. Part of the problem turned out to be related to the United States federal government shutdown that began in October 2025 due to political disagreements over budget negotiations, and this shutdown affected NASA operations, including the release of new scientific data and images from various missions. Because even though the spacecraft themselves continued operating autonomously in space and sending back data, the human scientists and engineers who process that data and prepare it for public release were furloughed and not allowed to work during the shutdown, creating a backlog of observations that couldn't be analyzed or shared with the public or the broader scientific community until the shutdown ended. This unfortunate timing meant that what should have been one of the most exciting moments in the study of 3I Atlas, the release of close-up images from Mars orbit that could reveal entirely new details about the comet's structure and composition, was delayed by weeks or potentially months due to circumstances that had absolutely nothing to do with science or space exploration and everything to do with political dysfunction on Earth. And astronomers and space enthusiasts around the world expressed frustration that bureaucratic problems were preventing humanity from learning more about this rare interstellar visitor during the brief window when it was close enough to study. Despite the delays and complications with the high-resolution Mars Reconnaissance Orbiter images, some data did emerge from other sources, including reports that China's Tianwen-1 orbiter had successfully photographed 3I Atlas during the Mars flyby, and that Chinese scientists were analyzing those images, though as of early November the images themselves had not been shared publicly through international scientific channels, and there was some discussion in the astronomical community about whether China would release the images immediately or would hold on to them for publication in scientific journals, which could take months. The Mars flyby represented more than just an opportunity to take pretty pictures. It was also scientifically valuable because the close approach distance meant that any spacecraft observing the comet would be able to measure its brightness and color and spectral properties with much higher precision than possible from Earth. And even if the images didn't show individual features on the nucleus, the photometric data could reveal information about the comet's size, how reflective its surface is, which is quantified by something called albedo, whether the brightness was changing over time, which could indicate rotation of the nucleus, or variations in outgassing activity, and whether the color of the coma and tail matched what was being observed from Earth-based telescopes, or whether there were differences that could indicate changes in the comet's activity or composition. The close approach to Mars also provided a natural experiment in gravitational interactions, because even though the comet wasn't close enough for Mars's gravity to significantly alter its trajectory, precise tracking of 3I Atlas's position before and after the encounter could potentially detect tiny deviations from the predicted path that would reveal information about the comet's mass, and knowing the mass combined with estimates of the comet's size would allow calculation of its density, which is a crucial parameter for understanding what the comet is made of, and whether it's a solid chunk of ice and rock or a more loosely bound rubble pile held together by weak gravity. After passing Mars, 3I Atlas continued on its inward journey toward perihelion, and the next opportunity for observations came from spacecraft that were in completely different parts of the solar system, but happened to have viewing geometries that allowed them to observe the comet as it passed behind the Sun from Earth's perspective. And one of those spacecraft was NASA's Europa Clipper, which had launched in October 2024 on a mission to explore Jupiter's ice-covered moon Europa, and was currently in the cruise phase of its journey. Positioned somewhere between Earth and Jupiter, where it had a clear view of 3I Atlas without the Sun blocking the view, the Europa Clipper carries cameras and spectrometers designed primarily for studying Europa's icy surface and thin atmosphere when it eventually arrives at Jupiter. But these instruments are sensitive enough that they could potentially observe 3I Atlas and measure its properties. And while the distance from Europa Clipper to the comet would be much greater than the distance from Mars during the October 3rd flyby, the spacecraft's position on the far side of the Sun from Earth meant it could observe the comet during the crucial perihelion period, when Earth-based telescopes couldn't see it at all, filling in a critical gap in the observation timeline. Similarly, NASA's Parker Solar Probe, which is on a mission to study the Sun by making repeated close passes through the solar corona, happened to be in a position where it could potentially observe 3I Atlas as the comet passed through perihelion. And while Parker Solar Probe's instruments are designed to study the Sun rather than comets, the spacecraft carries a wide-field camera called WISPAR, which images the solar corona and any objects that happen to pass through its field of view. And there was a possibility that 3I Atlas would be bright enough to show up in WISPAR images during the perihelion passage, which would provide valuable data about the comet's behavior at its closest point to the Sun, when heating and sublimation were at maximum intensity. The constellation of spacecraft observations from Mars orbit, from the Martian surface, from Europa Clipper in the outer solar system, potentially from Parker Solar Probe near the Sun, and from the James Webb Space Telescope and Hubble Space Telescope in Earth orbit, created an unprecedented multi-point observation campaign for 3 Atlas, with different spacecraft viewing the comet from different angles and at different distances throughout its journey through the inner solar system. And when all this data is eventually combined and analyzed, it will provide the most complete picture of an interstellar object ever obtained, showing how the comet's appearance and activity changed as a function of distance from the Sun, how its trajectory was affected by the gravity of the Sun and planets, and how its composition compared to comets from our own solar system. JWST. Right now, as you're reading this or watching this or listening to this, 3I Atlas is racing away from the Sun at a mind-boggling speed of over 210,000 kilometers per hour, which equals roughly 60 kilometers per second, or about 130,000 miles per hour. And it's moving on what astronomers call an escape trajectory, meaning it has more than enough velocity to break free from the Sun's gravitational influence and return to the vast emptiness of interstellar space, from which it came, never to be seen again by human eyes, unless we somehow develop the technology to chase after it with spacecraft that can match its incredible speed. The comet passed through perihelion on October 29, 2025, reaching its closest point to the Sun at 1.36 astronomical units, or about 203 million kilometers. And at that moment, it was experiencing maximum heating from solar radiation, which triggered maximum sublimation of the ices on its surface, releasing water vapor and carbon dioxide, and all the other volatile compounds that make up its ancient composition, creating what should have been the most spectacular display of cometary activity during its entire passage through our solar system, but unfortunately, we couldn't see any of it, because from Earth's perspective, the comet was directly behind the sun, lost in the glare of our star, hidden from view at precisely the moment when it was doing its most interesting things. After perihelion, 3I Atlas began the long journey back out of the solar system, and as it climbs back up out of the sun's gravitational well, it's gradually slowing down relative to the sun, though it's still moving at tremendous absolute velocity. And as it gets farther away, the solar heating decreases, and the sublimation slows down, and the coma begins to shrink and fade, and eventually the comet will return to its frozen dormant state, just a dark chunk of ancient ice and rock, drifting silently through space, carrying the secrets of its origin, locked in material that won't be disturbed again until it passes through another star system, billions of years in the future. If that ever happens at all. The comet emerged from behind the sun in early November 2025, reappearing in the pre-dawn sky before sunrise, and astronomers around the world immediately started observing it to see what had changed during its close encounter with the sun. And the first post-perihelion images were captured by Chinese astronomer Qicheng Zhang using the 4.3-meter Lowell Discovery Telescope in Arizona on November 3rd, just 5 days after perihelion, and those images showed that 3I Atlas had survived perihelion intact, which wasn't guaranteed, because some comets, especially first-time visitors from the Oort cloud that have never been heated before, can break apart or completely disintegrate when they get close to the sun, due to thermal stress and internal pressure from sublimating gases. The post-perihelion observations revealed that 3I Atlas was still active with a visible coma and showed evidence of continued outgassing, and some measurements suggested the comet might actually be brightening rather than fading, which would be unusual because typically comets reach their maximum brightness at or just before perihelion and then fade as they move away from the sun. But 3I Atlas has proven time and again that it doesn't follow typical comet behavior, so the possibility of post-perihelion brightening, while surprising, wouldn't be completely out of character for this weird object. One of the most intriguing developments that emerged from post-perihelion observations was the detection of what astronomers call non-gravitational acceleration, which means the comet's trajectory was deviating slightly from the path predicted by gravitational calculations alone. And this deviation indicated that 3I Atlas was experiencing some kind of force in addition to the sun's gravity. And the most likely explanation for non-gravitational acceleration in comets is the rocket effect caused by sublimating gases jetting off the nucleus surface and pushing the comet in the opposite direction, like a very slow and very weak thruster. Harvard astronomer A.V. Loeb, who has gained notoriety for his willingness to consider unconventional explanations for astronomical phenomena, including the possibility that some interstellar objects might be artificial probes sent by extraterrestrial civilizations, published a blog post analyzing the non-gravitational acceleration of 3I Atlas and calculated that the comet was experiencing a radial acceleration away from the sun of about 1.1 times 10 to the -6th astronomical units per day squared, along with a transverse acceleration of about 3.7 times 10 to the -7th astronomical units per day squared. And when you convert those numbers into more intuitive units, the combined acceleration amounts to about 94 kilometers per day squared at perihelion, which means that every day the comet's velocity was increasing by about 94 kilometers per day due to the rocket effect from outgassing. Loeb's analysis went on to calculate that to produce this level of acceleration, 3I Atlas would need to be losing somewhere around 13% of its total mass during the perihelion passage, assuming the ejection velocity of gases from the surface is around 300 meters per second, which is typical for cometary outgassing. and 13% mass loss is extremely high, much higher than typical comets experience during a single perihelion passage, suggesting either that 3I Atlas is much more active than normal comets, or that there's something unusual about how gases are escaping from its surface, or possibly that the comet is made of unusually volatile material that sublimates very efficiently when heated. The detection of non-gravitational acceleration is scientifically valuable because it provides a way to estimate the comet's mass through Newton's second law, which states that force equals mass times acceleration. So if you know the acceleration, and you can estimate the force from the outgassing rate, you can calculate the mass. And knowing the mass combined with estimates of the comet's size allows you to determine its density, which tells you whether the nucleus is made of dense rock and ice, or whether it's a loosely packed rubble pile with lots of empty space between the particles. The next major milestone in 3I Atlas's journey through the solar system will occur on December 19th, 2025, when the comet makes its closest approach to Earth, passing at a distance of 1.8 astronomical units, which equals about 270 million kilometers, or 167 million miles. And while that might sound close, it's actually almost twice the distance from Earth to the Sun, so the comet will be nowhere near us and poses absolutely zero threat of collision. And in fact, it will be so far away that it won't be visible to the naked eye and will require at least a moderately powerful amateur telescope to spot, probably something with an aperture of at least 6 inches and preferably larger to see the comet clearly against the background stars. For the few days around December 19th, amateur astronomers with appropriate equipment and dark skies away from city lights will have the opportunity to observe 3I Atlas and potentially photograph it. And while it won't be the spectacular naked-eye comet with a long, bright tail that captures public imagination like Hale-Bopp or McNaught, it will still be a once-in-a-lifetime opportunity to see an object that came from another star system, a visitor from the depths of interstellar space that has been traveling through the galaxy for billions of years before randomly passing through our cosmic neighborhood. Professional observatories around the world will be conducting intensive observations during the December close approach, using spectroscopy to analyze the composition of gases and dust being released from the nucleus, using photometry to measure how the brightness changes over time, which can reveal the rotation period and shape of the nucleus, using polarimetry to study the properties of dust particles in the coma, and using high-resolution imaging to capture the finest details of the coma structure and any jets or outflows that might be visible. After passing Earth, 3I Atlas will continue outward through the solar system, and the next significant encounter will occur on March 16, 2026, when the comet flies within 0.36 astronomical units of Jupiter, which translates to about 54 million kilometers or 33 million miles, and this will be the final close approach to any major planet before 3I Atlas leaves the solar system forever, and it represents one last opportunity for close-range observations from spacecraft currently operating in the Jupiter system. NASA's Juno spacecraft has been orbiting Jupiter since July 4, 2016, conducting detailed studies of the planet's atmosphere, magnetic field, and interior structure. And during the 3I Atlas flyby in March 2026, there's a possibility that Juno could be repositioned to capture images of the comet, though it would require careful planning, because Juno's primary mission is to study Jupiter itself, and reprogramming the spacecraft to observe other targets requires justification and coordination among mission planners. The Jupiter encounter is particularly interesting from a dynamics perspective because Jupiter is so massive that its gravity can significantly alter the trajectories of passing objects. And while 3I Atlas is moving fast enough that it won't be captured into orbit around Jupiter, the planet's gravity will slightly deflect the comet's path, tweaking its trajectory by a small amount that will affect where exactly it ends up in interstellar space. millions or billions of years from now. So in a sense, Jupiter will be giving 3I Atlas a final farewell nudge as it exits our solar system. After the Jupiter flyby, 3I Atlas will cross the orbit of Saturn in late 2026, then Uranus's orbit in 2028, then Neptune's orbit in 2029 or 2030, and by that point, it will be so far from the Sun and so cold and so faint that detecting it will be essentially impossible with current telescope technology, and it will fade from view, disappearing into the darkness between stars, just as it appeared from that darkness back in 2025 when Atlas telescopes first spotted it. The comet is expected to cross the heliopause, which is the boundary where the Sun's solar wind is no longer strong enough to push back against the interstellar medium, and is generally considered the edge of the solar system, sometime around January 2026, less than 2 years from now, and at that point, 3I Atlas will officially return to interstellar space, resuming the lonely wandering that was briefly interrupted by its passage through our solar system. The scientific significance of 3I Atlas cannot be overstated because this is only the third confirmed interstellar object ever detected passing through our solar system, and it's by far the most thoroughly studied of the three, with nearly 100 research papers published in just the first 4 months after discovery, more papers than were written about Oumuamua and Borisov combined in their first year. And this intensive study has revealed that interstellar objects are far more diverse than we initially thought, with 3I Atlas showing completely different characteristics from its two predecessors in terms of size, speed, trajectory, composition, and behavior. The discovery of 3I Atlas and the detailed observations we've made are already changing our understanding of how common interstellar objects are and what we can learn from them about planetary systems around other stars. And astronomers now estimate that there are probably hundreds or thousands of interstellar objects passing through the solar system at any given time. But most of them are too small, or too far away, or too faint to detect with current telescope systems, and we're only catching the rare few that happen to pass close enough and are large enough to spot. That situation is about to change dramatically with the full operation of the Vera C. Rubin Observatory, previously known as the Large Synoptic Survey Telescope, which is a revolutionary new astronomical facility located in Chile that features an 8.4-meter primary mirror and the largest digital camera ever built for astronomy, a 3.2 gigapixel camera that can image the entire visible sky every few nights and automatically detect anything that moves or changes brightness. And when Rubin Observatory begins full science operations, probably in 2026, it's expected to discover somewhere between 5 and 50 interstellar objects per year, maybe even more, compared to the current rate of roughly 1 interstellar object discovered every 3 years. So we're going from a trickle of discoveries to a flood, and each new interstellar visitor will provide additional data points about the diversity of planetary systems and the processes that eject comets and asteroids into interstellar space. The study of interstellar objects opens up an entirely new way of exploring the galaxy, because normally, when we want to learn about planets and comets around other stars, we have to use indirect methods like detecting the tiny wobble that a planet causes in its parent star's motion, or measuring the slight dimming when a planet passes in front of its star as seen from Earth. And these methods can tell us about a planet's mass and orbit, and sometimes its size, but they can't tell us much about composition or surface properties or what the planet is actually made of. But when an interstellar object passes through our solar system, we can point our most powerful telescopes and spectrometers at it and directly measure its composition. We can analyze the exact molecules present in the gases it releases. We can study the minerals in its dust. We can measure isotope ratios that reveal formation temperatures and conditions. And all of this information provides ground truth data about what actually exists around other stars rather than just theoretical models and indirect inferences. 3I Atlas is particularly valuable because its apparent origin in the thick disk population of the galaxy means it's giving us a window into planetary systems that formed 8 to 10 billion years ago, when the Milky Way was much younger, and the chemical composition of interstellar gas was different from what we see in newer systems like our own. And by studying this ancient comet, we can learn about what conditions were like in the early galaxy, whether the same types of ices and organic molecules existed back then, whether planet formation followed similar processes, and whether the building blocks of life were present in those ancient systems. The fact that 3I Atlas is so rich in carbon dioxide and contains complex organic molecules and shows evidence of billions of years of cosmic ray processing tells us that the basic chemistry of comets, the mixture of ices and rocks and organic compounds that makes them interesting from an astrobiology perspective, was already established billions of years before our solar system formed, which suggests that the ingredients for life might be widespread throughout the galaxy, both in space and time, present not just in many different stellar systems, but also across different epochs of galactic history. Looking ahead, the scientific community is already planning for the next generation of interstellar object studies, with proposals being developed for dedicated space missions that could potentially intercept and rendezvous with interstellar visitors. Though the extreme speeds and unpredictable arrival times make this technically challenging, and there are also proposals for rapid response telescope networks that could begin observing newly discovered interstellar objects within hours rather than days or weeks, maximizing the amount of data collected before the objects fade from view. The legacy of 3I Atlas will extend far beyond the data collected during its passage through our solar system, because it's demonstrated that interstellar objects are accessible to study with current technology, and that they provide unique scientific value that justifies the effort and expense of intensive observation campaigns. And it's shown that even though these objects are visitors from other star systems light years away, they're not fundamentally mysterious or incomprehensible. They follow the same physical laws and chemical processes that govern objects in our own solar system. They're just mixing those processes in different ways that reflect their alien origins. And by studying them, we're learning that the universe is both more diverse and more comprehensible than we might have imagined, full of endless variations on the same basic themes of gravity and chemistry and light.